Good morning, everybody, and welcome back to Abstract Algebra. So before I get into today's class, I just want to talk a little bit more about the online format I decided on. I decided not to do every day, kind of over Zoom, just kind of people like coming in, asking questions, because these are stressful times, especially because it looks like all your classes might be going online now, which may or may not be confirmed. Still waiting to hear from the college on that. But I don't know, I want to make things easy on you, but I also want to give you a chance to talk to me and ask questions and do stuff as a group. So I kind of decided we're going to do this one day a week. We'll be in person, not in person, but over Zoom synchronously, and then the other 2 days will be this sort of asynchronous, the pre-recorded videos. Just to try and strike a balance between trying not to stress you all too much, but giving you the chance to also kind of work together and still have somewhat of a class environment. So, oh my gosh, I forgot to change the agenda and stuff for my earlier class. So that's not your agenda, that's not your homework. I am lying to you. So your agenda is, we're going to start off by talking a little bit more about the first isomorphism theorem for rings, just doing a couple examples. And second, we're going to talk about a new type of ring, which is an integral domain, which is a special type of ring that's going to have some interesting properties to it. Your homework is just to finish up exam 2, which is due on Wednesday. And as far as office hours go, I have mostly my normal office hours. And those the way office hours will work will stay the same as back before we went fully online. You'll sign up on the link I posted on Blackboard, and then you can meet me over Zoom for those. Today and Wednesday, I'll have my usual office hours at 10 o'clock and from 2 to 3. Tomorrow, on Tuesday, I'm going to have to cut my morning office hour a little bit short because we have a department meeting at 11. So Tuesday morning, it'll be from 10 to 10:50, and Tuesday afternoon will be from 1:30 to 2:30. All right. What do mathematicians wear to keep the sun out of their eyes? They wear Divisor. Okay, so to start off, I want to do a quick little bit of review from last time. We said that a ring homomorphism is just a function between two rings, R and S, such that for all elements in the first ring, phi behaves nicely with respect to addition, meaning if you add and then apply phi to the sum, you get the same as if you take phi of A, phi of B separately, and then add those in the ring S. And it also needs to behave nicely with respect to multiplication, meaning if A and B are two elements in the ring, if you multiply A times B in the first ring and then apply the mat phi, you're always going to get the same thing as if you took phi of A and phi of B separately and then multiplied those two elements in the ring S to each other. And we said that if phi is a ring homomorphism, then the same first isomorphism theorem applies from group theory, that if you were to take R mod the kernel of phi in the quotient ring, R mod kernel of phi, that quotient ring is always going to be isomorphic to the image of phi. Which I wrote out in whichever notation you feel more comfortable with using. And today, I want to do a couple examples where we use the first isomorphism theorem, fit, to actually prove a couple ring isomorphisms. Or remember, a ring isomorphism, I didn't write this one down, but a ring isomorphism is just a homomorphism that's one-to-one and onto. Similar for group isomorphism. So an isomorphism just means we have one of these, a function phi satisfying both these conditions, that's also one-to-one and onto. So let's see if we can look at this. So here, I'm going to let S be the set of all integer polynomials. So recall, this is the set of all polynomials whose coefficients are integers. We take the set of all integer polynomials whose constant terms are 0. So something like x cubed plus x squared minus 15x plus 0 would be in S, but something like x cubed plus x squared minus 15x plus 27 would not be in S. If S is this set of things, I'm not going to prove it, but S turns out to be an ideal in the ring of all integer polynomials. That's something you could prove for a little bit of extra practice. Then it's going to have to be the case that if you take the ring of all integer polynomials and mod out by S, you're going to get a quotient ring that is just isomorphic to the ring of integers. So let's see if we can prove this. So first isomorphism theorem proofs for rings are very similar to how they worked for groups. We're going to need to find a ring of homomorphism from this group, the group we're quotienting out by, to this group. So we're going to define a map Phi that goes from the ring of all integer polynomials to the ring of all integers. And we want Phi to be a ring homomorphism that is onto and whose kernel is equal to S. So in other words, the set of all things mapping to the identity element in Z, which is just the integer 0, we want the set of all things mapping to 0 to just be at the set S, the set of all integer polynomials whose constant terms are 0. So what would be a way to map an integer polynomial to an integer in a way that polynomials whose constant term are 0 is going to map to the integer 0? What's that, Nick? Map the polynomial to its constant term? What a great idea. So we're going to define our map Phi by Phi is going to take in any integer polynomial and it's going to map it to just A0, the constant term of that polynomial. And we're going to show then that Phi is a ring homomorphism that's onto and whose kernel is equal to S. And once we have all those pieces, that'll then tell us that from the first isomorphism theorem that this quotient ring has to be isomorphic to this ring. All right, Meg. No, I'm not going to ask Megan again. All right, Philip. Which one do you want to prove first? We need to show Phi is a ring homomorphism, that its kernel is S, and that Phi is onto. Starting with Phi is a ring homomorphism. That's a good idea. See, Megan, that's why I don't ask you anymore. So let's show that Phi is a ring homomorphism. So to do that, we need to show two things. We need to show that Phi satisfies both conditions of the ring homomorphism. Well, that's going to come out from if f of x is of the form an x to the n plus a sub n minus 1 x to the n minus 1 plus a1x plus a naught, and g of x, which we'll say is b sub m x to the m plus b sub m minus 1 x to the m minus 1 plus b1x plus b naught. If these are two arbitrary integer polynomials, then first of all, if we were to take Phi of f of x plus g of x, well, what would that be by definition? That would be Phi of an x to the n plus blah 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 plus a naught plus bm x to the m plus blah 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 plus b naught. What's the constant term of this polynomial going to be? The polynomial we would get from adding these two f of x and g of x together. That's right. The constant term would just then be a naught plus b naught, because all the other terms in this sum are going to have x's in them. And a naught plus b naught is just going to be Phi of f of x plus b of g of x by definition. So we have one of our two conditions for ring homomorphism. The other condition we can show fairly quickly by saying also Phi of the product f of x times g of x is going to be Phi of, oh goodness, an x to the n plus blah 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 plus a naught times bm x to the m plus blah, 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 plus b naught. If we were to multiply those two polynomials together, what would be their constant term? Well, every term in this product is going to have at least one x in it, except for what happens when we multiply the constant term in the first polynomial by the constant term in the second polynomial. And thus, when we multiply the two polynomials together, the constant term of this product is just going to be a naught times b naught, which is just going to be phi of f of x times b of g of x, by definition. Neato mosquito, we have shown that our map phi here is a ring homomorphism. We still need to show two other things. We still need that phi is onto, and that phi is a kernel of S. Let's show that the kernel of is S next. Need to make some room here. Thank you, definitions. You helped out a lot. So here we need to show that the set of all things mapping to 0 is precisely the set S. So by definition, the kernel of phi is going to be the set of all polynomials in our original ring, the ring of integer polynomials, such that phi of p of x is going to be the additive identity in the ring of integers. So what is the additive identity in the ring of integers? Well, that's just going to be 0. The set of all integer polynomials p of x such that phi of p of x is 0. But what does that mean, to say that phi of p of x is 0? Well, since phi of p of x is the constant term of p of x, that's just going to be the set of all p of x such that p of x has constant term 0. Which, of course, by definition, is just going to be S. Boom! We've proven that the kernel is S. The set of all things mapping to the additive identity of the integers, ring of integers, is just this ideal S. And so finally, we have one more thing we need to check. We need to check that phi is onto, which phi onto is going to tell us that the integers is precisely equal to the image of phi. So here we need to show that given any element, let's say A, in the codomain, the ring of integers, we need to find some integer polynomial that maps to A under phi. So what would be an integer polynomial that would map to A under the mapping phi? Phi of blank is A. What's that, Nick? A is equal to phi of 27x cubed minus 15x squared plus 49 billion x minus 2, plus A? Okay, yes, that's technically correct. Let's do a simpler one. Let's say phi of x plus A. That's certainly an integer polynomial, assuming A is an integer, x plus A has coefficients that are all integers, that if we were to take phi of x plus A, we would just get back A. All right, so we've shown that phi is onto. And thus we can say, thus, by the first isomorphism theorem, z of x mod the kernel of phi has to be isomorphic to the image of phi. But since the kernel of phi is S, this is the same as saying that the integer polynomial modded out by S has to be isomorphic to the image of phi. And since phi is onto, meaning the image of phi is going to be equal to the entire ring of integers, is giving us what we want. The ring of all integer polynomials modded out by S has to be isomorphic to the ring of integers. The same basic procedure for how to use the first isomorphism theorem for groups to show a quotient group is isomorphic to some other group. We just have to find some homomorphism from the group getting quotiented out by to the other group, to the group we want the quotient group to be isomorphic to. In this case with rings, you need a homomorphism from integer polynomials to Z. First, we need to show that that's actually a homomorphism. For groups, we only need to check one thing to have a homomorphism. For rings, we would need to check two things. And we need to show that that homomorphism has a kernel equal to the thing we're quotienting out by, in this case S. And we need that our homomorphism is onto in order to get that the image of phi is equal to the thing you want it to be. And thus, boom, big bop, boom, big bow, we have a ring isomorphism using the first isomorphism theorem. In our what do I call it? I don't know, in our Zoom class on Wednesday, I'll have you all work through the last example on this page. One involving matrix rings in Z mod 3Z. But I'll let you, I'm going to save that for class Wednesday. If you want to think about it in the meantime, you're welcome to do so. All right, that's going to do it for this packet. So next up, I'm going to go back a chapter and start talking about chapter 11, chapter on integral domains. So if you've noticed, everything that we've done so far in ring theory has kind of been a generalization of something we did back in group theory. So we had ideals, same basic idea as normal subgroups. We had ring homomorphisms, just like we had group homomorphisms. We have quotient rings, just like we have quotient groups. We have first isomorphism theorem for rings, just like first isomorphism theorem for groups. So today, in the rest of today's class, we're going to start talking about things related to rings that don't really have a nice correlation with groups. In particular, we're going to be talking about something called zero divisors, numbers in rings that divide zero. But Dr. Gerstill, nothing divides zero. In ring theory, stuff does. We're going to talk about zero divisors and then a special type of ring called an integral domain that is made up of these so-called zero divisors. So let's write down some definitions. This is a new packet on integral domains. It's up on Blackboard by the time you're watching this video. Should be. If not, send me an email saying Dr. Gerstill, you forgot to post the integral domain packet. So first of all, we're going to define zero divisors. Given a ring R, we say a zero divisor of R is a non-zero element A in our ring such that A times B is equal to 0 for some B not equal to 0 in our ring. Or we could have that B times A equals 0. So in other words, zero divisors are basically non-zero elements in our rings that we can multiply together to get the zero element in that ring, the additive idea. But Dr. Gerstill, if we have two non-zero things, how can they multiply together to give us 0? Well, let's look at a quick example of what zero divisors would look like. And I want to look in the ring, let's say our ring is, I don't know, Z mod 8Z. I claim I can find two elements in Z mod 8Z that are not equal to 0, but nonetheless will multiply to give us the 0 element. So remember, Z mod 8Z It's made up of the elements 0 bar, 1 bar, 2 bar, 3 bar, red bar, blue bar, 2 bar, blue bar. 0 through 7 bar. 8 elements in this ring, which we can add and multiply mod 8. What are going to be two things in this ring that would multiply together to give us 0? Neither of which are 0 to start with. Well, I think 2 bar and 4 bar will do the job. Because we can take 2 bar and multiply by 4 bar, and that would give us 0 bar, i.e. the additive identity in this ring, even though 2 bar and 4 bar themselves are not equal to 0 to start with. Thus, we have two non-zero elements in our ring that are multiplying together to give us the 0 element, the additive identity in our ring. Thus, 2 bar and 4 bar are 0 divisors. In the ring Z mod 8. It's because there are numbers that are not 0 and that you can also multiply by some other non-zero thing in order to get the 0 element. So here's a question. Are there any elements in Z mod 8Z that are not 0 divisors? Things in this ring that you can't multiply by anything non-zero to get 0. I find there are a few. And one of which is going to be 1 bar. Because if you notice, if there's 1 bar times x, if you try to multiply 1 bar by something in the ring and get 0 bar, there's nothing you can multiply 1 bar that will get you 0 bar other than 0 bar itself. Because we multiply by 1 bar, we get 1 bar, 2 bar, we get 2 bar, 3 bar by 3 bar. No matter what element in the ring we take, we're just going to get back that element when we multiply by 1 bar. And so we could say, since 1 bar times x is 0 bar, as only x equals 0 bar as a solution in this ring, one bar is not a 0 divisor in Z mod 8Z. Because there's no non-zero elements in our ring we can multiply 1 bar by in order to get 0. Whereas 2 bar and 4 bar, there are totally non-zero things we can multiply each of those by to get 0 bar, namely the other thing. 2 bar has 4 bar, 4 bar has 2 bar, L bar, and so 2 bar and 4 bar are 0 divisors, but 1 bar is not. Because there's nothing non-zero we can multiply 1 by to get to 0. All right, so what I'd like for you all to do is take a couple minutes and look through these examples of rings that I'm going to give you on the front page. Specifically, erase this, give myself some room. I want you all to look at the ring of all real numbers, the ring of all 2 by 2 real matrices, the ring Z mod 12Z, and the ring of all continuous functions over the rings. I want you to take a couple minutes and see if you can tell me which of these rings have 0 divisors in them. Can you find examples of 0 divisors in these rings? If not, why not? And if so, give me a couple examples. Let's go ahead and take a couple minutes, pause the video, see if you can work this out, and then we'll talk about this when we come back to the video. I'm going to freeze in place for a second so you can pretend, so that you know this is a good place to pause, and try and find 0 divisors in each of these 4 rings. Okay, you're back there, which means you've taken a couple minutes, you paused the video to find some 0 divisors. If not, do that now before continuing. How about the real numbers? Does the ring of all real numbers have any 0 divisors? The answer is no. Because we can say in this ring, if A times B is equal to 0, then A equals 0 or B equals 0 in the ring of all things. Meaning it's impossible to multiply two non-zero real numbers together to get 0. How about in the ring of all 2 by 2 real matrices? Are there any two non-zero matrices that will still multiply together to give us 0? I think the answer to this one is going to be yes. And as an example, we can say that 1, 0, 0, 0 is a 0 divisor. Since 1, 0, 0, 0 is a matrix we can multiply by some other non-zero matrix. Non-zero here meaning at least one term in the matrix is non-zero. We can find another 2 by 2 matrix that we can multiply 1, 0, 0, 0 by that's not the zero matrix, but that will still give us a product of the zero matrix. And I think matrix that'll work is this one. If you do your matrix multiplication here, neither of our two matrices were the zero matrix to start with, but they multiplied to give us the zero matrix. So 1, 0, 0, 0 is a 0 divisor. And by the same logic, this one will also be a 0 divisor, 0, 0, 0, 1. All right? So here is Z mod 12. Let's look at Z mod 12Z. I think similarly to Z mod 8Z, we can find some 0 divisors in this ring. Let's say, I don't know, how about 3 bar? 3 bar is a 0 divisor because I claim you can find some element in the ring, a non-zero element, such that 3 bar times that thing is the 0 element. What can you multiply 3 bar to get 0 bar? Why 4 bar, of course. Since 3 bar times 4 bar is, in fact, the additive identity. There's a non-zero thing we can multiply 3 bar to get to 0 bar, thus 3 bar is a 0 divisor. And similarly, 4 bar is also going to be a 0 divisor in this ring. All right, here's the one that I'm sure you all were too scared to try. Chickens. I hope you tried this one. It's a fun one. Are there non-zero functions other than the constant function y equals 0 in the ring of continuous functions over the reals that are 0 divisors? Non-zero functions that multiply by other non-zero functions to give you the constant y equals 0 function. As a matter of fact, there are 0 divisors in here. Specifically, if we were to take f of x is the piecewise function 0 for x less than or equal to 0, and x if x is greater than 0, meaning f of x is a function that looks like this. And g of x is a function that looks like this. X for x less than or equal to 0, and 0 for x greater than 0. Let's make it negative x. Just throw a little bit of whimsy. So these are both not the 0 function. They're both non-zero for some values of x. If you notice, f of x times g of x, though, will always give the 0 function. Because if x is negative, f of x will be 0, so f of x times g of x will be 0. If x is positive, g of x will be 0, so f of x times g of x is 0. If x is 0, well then both f of x and g of x are 0, so the product will be 0. F of x times g of x is 0, even though f of x and g of x are not the function that's always 0 everywhere. Their product is always 0 everywhere. So f of x and g of x are both 0 divisors. Awesome, possum, lemon blossom. Let's do another example. I would like to look at a special type of ring now, or not example, let's say example. I want to look at a special type of ring now where there are no zero divisors. And the ring I would like to look at specifically is going to be this a ring called an integral domain. So an integral domain is going to be a special type of ring that has some nice properties to it. It's going to be a ring R such that, first of all, R is commutative. Dr. Gersel, what do you mean by a commutative ring? Rings have to have two operations. Which operation are you referring to when you say the ring has commutativity? Well, since the addition operation has to be commutative by definition, A plus B always has to be B plus A. When we say that a ring has commutativity, we mean that multiplication is commutative. I.e., A times B is equal to B times A for all A and B elements in your ring. So that's the first thing we want in an integral domain. Second thing we want is that your ring has multiplicative identity. There's some element 1, a multiplicative identity in your ring. It doesn't have to be the integer 1 or the real number 1, but something that serves as the multiplicative identity. And finally, R has no zero divisors. So in other words, if A times B is equal to 0, then it has to be the case that at least one of the two elements is 0. Then A equals 0, or B equals 0, or potentially both. So integral domain is kind of this ring with nice properties of no zero divisors, it has a multiplicative identity, and the multiplication operation is commutative. A times B has to always be B times A. So, as a quick example, what would be an example of a ring that is an integral domain? Well, probably the easiest example to look at is the ring of integers. Because if you look at integral domain, the word integral is not being said it's super important, though it is. Integral here just means like the integers as an adjective. Integral domain is a ring that behaves like the integers, because the integers have all these properties. Multiplication is commutative, there's multiplicative identities, the integer one specifically in this case, and there's no zero divisors, meaning if you have two things that multiply to give you 0 in the ring of integers, at least one of those two integers has to have been 0 to start with. There's no way you multiply non-zero integers to give you 0. So the ring of integers checks out. Let's see. What would be a ring that does not check out? Z mod 12Z does not check out. Why is that? Well, Z mod 12Z is commutative. Multiplication mod 12 is commutative. There is a multiplicative identity, namely 1 bar, but Z mod 12Z does have 0 divisors. This is not an integral domain. Integral domain. I'm not going to use ID because we've been using ID all semester to say identity. But the Z mod 12Z is not an integral domain since this ring has 0 divisors. And so, let's take another look at a couple quick examples to see if we can find a few rings that are and a few rings that are not integral domains. So rings I want to look at are going to be ring of all 2 by 2 real numbers, the ring of all real number polynomials, Z mod 6Z, and Z mod 5Z. So just like before, I want you to pause the video and see if you can determine which of these rings are integral domains and which ones are not. Go pause the video, think about that for a minute, and when we come back, we'll talk through. Okay, I assume you thought through these 4 examples, and then you pause the video. If not, do so now. Let's talk through each one of these rings. So, ring of all 2 by 2 real matrices is not an integral domain. You know what? I'm just going to say ID. No, I'm not going to say ID. Why not? Dr. Gersel, don't be stupid. This is not going to be an integral domain. So why not? Which conditions does it fail? Well, it actually fails 2 different conditions. It has 0 divisors, as we saw on the last page, but it also is not commutative. Matrix multiplication doesn't work both ways. A times B does not have to equal B times A. So, since matrix multiplication is not commutative, it's going to be my reason for why this is not an integral domain. Also, if you wanted to, you could also say it's not an integral domain because it has 0 divisors, for instance, 1, 0, 0, 0, and that would be another valid reason as to why this is not an integral domain. How about the ring of all real polynomials? Well, real polynomial multiplication is commutative. F of x times g of x is going to give us g of x times f of x. Has multiplicative identity. This is the identity function. F of x equals 1. The constant function y equals 1 is multiplicative identity in this ring. And finally, it doesn't have any 0 divisors. If f of x times g of x is 0, then one of those 2 functions has to be 0, assuming you're looking at polynomials. A little bit hard to show that polynomials like that have 0 divisors, but it does turn out to be the case. You can make an argument using the fact that the degree of f of x times g of x is always going to be the degree of f of x plus the degree of g of x, which means the only way to multiply 2 non-zero polynomials and get a constant is just going to be if those 2 polynomials are constants to begin with. And if you take 2 non-zero constant polynomials and multiply them together, you're going to get something else non-zero. Mainly because the ring of all real numbers is an integral domain. How about Z mod 6Z? That certainly has commutativity, has multiplicative identity. This is going to be an integral domain. Nope. It's going to not be an integral domain because it does have 0 divisors. Since it has 0 divisors. And as an example, we could say 3 bar, since 3 bar times 2 bar will give us 0 bar in this ring. So it has 0 divisors, it's not an integral. Alright, how about Z mod 5Z then? Multiplication mod 5 is commutative. 1 bar is multiplicative identity here. So does Z mod 5Z have any 0 divisors? 1 bar has nothing we can multiply to get 0 bar other than 0 bar. 2 bar has nothing we can multiply to get 0 bar other than 0 bar. Same ditto with 3 bar and 4 bar. This one actually checks out. If we make a quick Cayley table, zero, 1, 2, 3, 4, 5, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 2, 3, 4, 5. Oh my gosh, it's being stupid. This is Z mod 5Z, not Z mod 6Z. So yeah, it's just a 5 by 5. 0, 4. 2 bar times 2 bar is 4 bar. 2 bar times 3 bar is 6 bar, which is equal to 1 bar. 2 times 4 is 8, mod 5 is 3. 3 times 2 is 6, mod 5 is 1 bar. 3 bar times 3 bar is 9 bar, mod 5 bar is 4 bar. 3 times 4 is 12, mod 5 is 2. 4 times 2 is 8, mod 5 is 3. 4 times 3 is 12, mod 5 is 2. And 4 times 4 is 16, mod 5 is 1. If you notice, in this ring, the only way to multiply two things to get 0 bar is if at least one of those two things is 0 bar itself. There's no way that we can multiply, this is multiplication mod 5. There's no way we can multiply any two non-zero things and get 0. Which we know from the fact that if we look at the non-zero rows and columns, we multiply them out, there's no zeros bars involved. So Z mod 5Z is an integral domain, but Z mod 6Z is not. That is most peculiar. All right, that's going to do it for today's class, I think. When we come back on Wednesday, in our class on Wednesday, I'm going to have you explore the question of why was Z mod 5Z an integral domain, but not Z mod 6Z? When, in general, can we say that Z mod NZ will form an integral domain? All right, hope you all have a good rest of your day. See you all on Wednesday.